One day our universe is going to end. The last stars are going to fade away. And with them, any memory of what was once a colorful and vibrant universe. And it doesn't matter what we do or where we run to, even if humanity lasts forever, we're gonna need to adapt to get past this hurdle. And for that purpose, we're going to need to learn how to live around a black hole. But is that even remotely possible? In this video, we're indeed going to learn that yes, it is, as long as certain conditions are met.
Hey, Pedro here. This video you are watching was originally in Portuguese, my native language. This is the attempt of our team to translate it to English, and I sincerely hope you enjoy it. Your feedback is extremely important to us. Now, back to the video.
First try. Let's commence quite simply. Let us pick a black hole that's got a planet orbiting it. In this first case, the black hole is of stellar origin, so it's not actually some galactic monster like the black hole at the center of our galaxy, but rather essentially a black hole with a few times the mass of the Sun. And the planet is just like Earth. Just a fun fact. If the Sun turned into a black hole with the same mass as our star has now, all the planets would keep orbiting just the same. And I can see you typing in the comments cussing me out, but it's true. The main difference is that the Sun would be squished down until it's just a tad bigger than Mount Everest. It'd also lose its shine. There's absolutely no risk of jets or winds here, because the black hole isn't currently munching on anything at all. Even Hawking radiation, which is the process that makes black holes slowly evaporate, is slow enough not to directly affect the planet. Everything seems perfect up to now, right? Nope. Not even a month later we realize that civilization on the planet is no more. Humanity has hit total extinction. Since it's a planet that doesn't get any energy source, it's a frozen world and uninhabitable. It's impossible to grow food on the surface. The temperatures are way too low for life as we know it. The entire planet turns into a kind of frozen wasteland, with hardly any sign of life whatsoever, and that indeed was our gravest mistake in selecting this planet. We were so caught up in looking for something Earth-like and the dangers of a black hole that we forgot about the most important part. There isn't a heat source other than the planet itself, which just isn't enough. But relax, let's pretend like this never happened. We still got a few tries left. Second try. This time, we're going with a stellar black hole again, which means one that's just a few times more massive than our Sun, with a planet akin to Earth orbiting it. But unlike the previous attempt, we're going to assume this black hole is consuming a companion star, an X-ray binary. Now we are talking. The accretion disk that forms around the black hole acts as a heat source, just like the star that's getting gobbled up. But a curious fact starts to emerge. The planet's orbit is kind of weird. It doesn't seem to follow an orbit, really. At least not in the way we're typically used to, with almost perfect circular orbits encircling the Sun. But the planet's been hanging around a black hole all this time, so it somewhat feels like we can indeed just brush that off, right? Maybe the orbit is following a pattern that we just can't pick up on at first glance. What matters is that this time the surface isn't frozen. We even managed to spot liquid water and something green on the planet, pretty much like how we see Earth from space. Right off the bat, we noticed that civilization adapts pretty well under these conditions, even though it's hotter than back on Earth. Looks like we finally got it right and learned from our past mistakes, finding a spot for humanity to thrive around a black hole. Until we try to examine the system again, and the planet is nowhere to be seen. And after checking out images from telescopes, we realized that an energetic wind broke free from the black hole star system and hit the planet dead on. And that fried its atmosphere and changed the course of its orbit, which made it get too close to the black hole and get swallowed up in the process. In a matter of days, the planet turned into spaghetti and got sucked into the black hole. And just when we thought it couldn't get any worse, the star blows up a few years later, because the black hole gobbled up a bunch of its matter, making it collapse. Even if it weren't for the energetic winds the black hole spews out, the planet would probably end up getting swallowed eventually. This is the famous three-body problem. Indeed, the movement of the orbits ends up becoming chaotic. Even if the planet hadn't been completely swallowed up, the star's explosion would have certainly fried it, or at the very least booted it out of the star system, doomed to freeze in the vastness of space. Okay, looks like we're indeed hitting a pattern here. Maybe, just maybe, the problem is related to stellar black holes. They can actually be more dangerous than the supermassive ones, and that's an undeniable fact. Indeed, it's pretty much impossible for any orbit to remain stable for that long around stellar black holes. Any little thing could throw the entire planet off course. And any civilization on the surface would be far too vulnerable because of that. Third try. This time we're gonna do it right. Instead of a tiny black hole with just a few times the mass of a star, we're going to grab a supermassive black hole with millions of times the mass of the Sun. And to keep us from freezing, let's say this black hole is absorbing at a super high accretion rate. What would happen to a planet orbiting that black hole? First off, we have got to consider that it's going to be far enough away from the hole and, yep, even before we chose the planet, it was zapped by radiation, erasing its atmosphere. But we've a name for black holes feeding on high accretion rates. Quasar. They're so extraordinarily bright that when they were actually first discovered, a lot of astronomers indeed mistook them for stars. Looking at this picture here, can you tell which one's the quasar 9 billion light years away from us, and which one's the star just a few light years away? If you said the quasar is the one on the left, congrats, you nailed it. Black holes that absorb at a high accretion rate can be thought of as quasars. The problem with attempting to find a comfortable spot around a quasar is that they're super energetic, significantly more energetic than a planet could possibly handle. A good chunk of the spectrum from a quasar like this is in wavelengths of X-rays, ultraviolet, and even gamma rays. And I reckon you can already picture that. Even if we managed to wrap civilization around one, it'd be a pretty inhospitable place for humans. So let's steer clear of hungry supermassive black holes. Fourth try. Now we're going to pick a supermassive black hole, but with a low accretion rate, kinda like the one in M87 star, which is the first black hole we snapped a picture of. This black hole is really similar to Gargantua from Interstellar. And if you've seen the movie, you know planets can orbit it. And I know movies often get their science facts wrong, but in this one, physicist Kip Thorne, who's bagged a Nobel Prize, helped pick the kind of black hole that could host life-bearing planets with habitable zones around it. The habitable zone of an object is the area where liquid water can exist, and every object has a habitable zone. If we put a planet in orbit around that black hole, we'd have a situation pretty much like what goes down in Interstellar. And just like in the movie, everything seems to work out. The planet can't be too close to the black hole because energetic winds are getting blasted out all the time. And they've got enough power to make the whole planet go poof. Instead, we're going to carefully put the planet in a spot that's a bit more comfy and further away. And at first, everything seems to work out. We've got a nice temperature and a power source coming from the black hole's accretion disk. It even lights up the sky. The only downside seems to be the weather. It's like there's no temperature gradient at all. The whole planet is always at the same temperature, and that happens because this planet only gets one specific wavelength, which is just enough to keep it nice and toasty. Besides, there isn't an exact definition of a year or a day, because due to gravitational effects, light's all over the globe all the time. Okay, but I think at this point we could agree that, well, it could be worse. At least it seems like a place where you can keep on living even with these hurdles. But over time, any civilization living on a planet like that would realize it's pretty tough to grow food. People would get sick a lot, and the birth rate would plummet. In no time, civilization would meet its end, since many wouldn't be able to survive that system. And that's pretty amazing, and indeed somewhat unexpected, because it actually seemed to be exactly the kind of place we were looking for. In the habitable zone, safe from any energetic stuff hitting the planet, plenty of energy. So we racked our brains trying to figure out what happened, and finally we got it. Some complex molecules essential to life need photons of different energies to be broken down. Hear me out. We actually know that the sun has a peak radiation emission in the visible spectrum, which is really enough to power us up here on Earth. But the sun also emits, at somewhat lower intensities, both more energetic waves and less energetic waves. But as much as some of those photons are too energetic for us, like UV radiation for example, they're still crucial for breaking down and transforming molecules that are essential for life. When we put the planet in a spot where there's only one wavelength coming through and just one temperature, at some point that was going to mess with humans. It's an indirect and unexpected consequence, but it would still lead the civilization around the black hole to collapse. So once again, we're gonna reset our experiment, because it hasn't worked out yet. Fifth try. Now we're gonna pick a supermassive black hole that's got an accretion disk that's not too busy, just like the last example. But this time we're going to place stars all around, stars that are not only bright but also truly massive. The only reason the last civilization didn't pan out was because of the lack of more energetic photons, because otherwise, all the conditions were favorable. Another piece of good news is it's more common to find supermassive black holes surrounded by stars, meaning this black hole we just made in this example is a common type in the universe, easy to stumble upon. Besides, the view on the planet must be beautiful. A sky filled with stars. more than we got here on Earth in all sorts of colors. That's way too many stars. This makes us realize that the planet's sky is exceptionally luminous, making it impossible to even look up. Imagine if up in the sky here on Earth we had the sun, but like thousands of times brighter. And now we're going to multiply this a bunch of times until we got stars taking over the whole sky. It'd be downright impossible to even step outside, and even holing up somewhere wouldn't help. There are particles called neutrinos, and trillions of them are zipping through your body right now. They're known as silent killers, precisely because they barely interact with anything around them. And here, around the sun, our closest source of neutrinos, they're never ever going to be a problem for us. But if we had thousands of suns luminous and shining right next to us, that'd be a problem. They're so full of energy that it can mess with the planet's chemistry and atmosphere, not to mention humans themselves. It's kind of disheartening to know we got so close to success and then something invisible just smashes our hopes. But there's one last shot, one final attempt. So, let's circle back to the beginning of the video one more time, to give it our utmost attention. Last try. This time we're going to go all out picking a supermassive lonely black hole. It's not absorbing anything, and there aren't even stars nearby. Hawking radiation is so weak that it's pretty much imperceptible. It doesn't mess with anything on the planet. At first glance, this scene doesn't seem to have any livable spots, especially since the black hole doesn't provide any source of energy. And this might look a lot like the mistake we made on our first try, especially since the big issue with that attempt was the planet not having a power source and ending up freezing over. But let's wait just for a moment, because I'm about to lay out why we're opting for this choice. To truly get you on board with this being our absolute best shot, I need you to think about the movie Interstellar and how they brilliantly tackle that whole time warp conundrum. Basically, when two astronauts head to a planet near the black hole, time for them moves way slower. When they get back to the ship, they realize years have gone by, while for them it was only a few hours. And that really happens, and it's even measured right here on Earth, obviously in a way less intense. But what few know is that this effect applies to light wavelengths too, and right here's the perfect spot to give an example. Imagine the astronaut who stayed on the ship is sending a signal every second. The astronauts on the planet are going to get 60,000 signals a second, because 2 hours on the planet is like years on the ship. Now turn that into the frequency of light. If the astronaut in the spaceship sends out a low-frequency light signal, the astronauts on the planet will receive that signal at a much higher frequency. Higher frequencies mean more energetic photons, which can essentially heat up the planet, much like how the sun does us. And the universe itself offers a frequency, a residue of the Big Bang, called cosmic microwave background radiation, or CMB. For us here on Earth, the cosmic background radiation is almost imperceptible, with its mere 2 Kelvin temperature, or minus 271.15 degrees Celsius. We can only measure it with special telescopes. But for a planet close enough to a black hole, the cosmic background radiation could be stretched out to wavelengths similar to the sun's. In other words, the cosmic background radiation would be like the sun in the sky. It would work as a power source for the planet, even making it possible for liquid water to exist. So, okay, we solved the energy problem. The issues tied to a potential wipeout by a black hole munching on stars have already been squared away, because now we're in a safe zone. Civilization could live around this black hole. The only hitch is that day and night wouldn't really be a thing for this planet, since cosmic background radiation comes at it from all corners of the universe. So the entire planet would be completely enveloped in this artificial star, creating a unique effect in the sky. The seasons would all be the same too. The very idea of a year wouldn't even exist. It'd be the same weather all year round. It'd be like living in an endless blissful summer forever and ever. A planet where future generations wouldn't know dark skies. Maybe only by the spot in the sky where the black hole is could this civilization get a clue about having a dark sky, or at least a piece of it. And of course, even that wouldn't last forever. Eventually, something might make its way to the black hole, even if it took hundreds of thousands of years. Besides, cosmic microwave background radiation would weaken over years as the universe cools. This would indeed take a good while, but it'd also have an expiration date. So, it'd actually be like a temporary-based shelter for humanity. If the question is whether we could live around a black hole, then, under extremely specific conditions, the answer is yes. But that would be so specific, so specific, it's even hard to find a system like that in the universe. But the universe is vast. There's a non-zero chance that there's some system like that out there. For me, the takeaway from this video is that no matter how advanced our technology becomes or how much we understand the cosmos, we're never going to be able to become immortal. We have to accept it. Thanks a bunch and see you next time.